This problem explores how to interpret results from sklearn's validation_curve function, which is used to assess how changes in a model's hyperparameters impact its performance. Specifically, it focuses on a support vector machine, SVM, classifier using a radial basis function, RBF, kernel and tuning the gamma hyperparameter. The goal is to understand how different gamma values affect the training and validation accuracy and to identify potential overfitting. This shows the accuracy scores of the SVM model on the training data for different gamma values. Each inner list represents the accuracy for a particular gamma value, with 3 different runs, folds. The scores suggest the model's accuracy increases with increasing gamma. These are the specific training accuracy scores for 3 different gamma values: 0.1, 1, 10. Each inner list provides the accuracy for each gamma across 3 separate runs, possibly for cross-validation, showing improving training accuracy as gamma increases. Similar to training scores, these represent the accuracy of the model on a separate validation dataset, which is crucial for evaluating generalization performance and preventing overfitting. These are the validation accuracy scores corresponding to the gamma values 0.1, 1, 10. Note that unlike the training scores, validation accuracy initially increases and then decreases. These are the different values of the gamma hyperparameter used in the SVM. Gamma controls the influence of each data point. Higher gamma values lead to more complex decision boundaries. This section presents a multiple-choice question testing your understanding of how to interpret the training and validation scores to determine model performance and the impact of the hyperparameter gamma. The core question asks you to analyze the data provided and identify which statements are true. This requires evaluating how the training and validation accuracies change with gamma, and recognizing the signs of overfitting. This statement is evaluated by looking at how both training and validation accuracies change as gamma increases. Are both consistently getting better, or is there a different trend? This statement focuses on assessing the difference between training and validation accuracy as gamma increases. A large difference can suggest the model is overfitting, performing well on the training data but poorly on unseen data. This checks the validation accuracy for each gamma value and determines if gamma equals 1 produces the best result. This statement assesses whether training accuracy consistently exceeds validation accuracy across all gamma values. A key indicator of overfitting, model complexity is too high. This statement analyzes whether increasing the gamma hyperparameter in the support vector machine, SVM, consistently improves model performance on both the training and validation datasets. Let's look at the provided data. The training accuracy does increase with gamma, but the validation accuracy increases initially and then decreases. Thus, the improvement is not consistent across both datasets, making the statement false. This statement explores whether the model exhibits overfitting as gamma increases. Overfitting occurs when a model learns the training data too well but performs poorly on unseen data. The provided training and validation scores show that the gap between the two increases with increasing gamma. This widening gap signifies overfitting, making the statement true. This assesses the optimal gamma value based on the validation accuracy. Remember, we're primarily interested in how well the model generalizes to new data, which is represented by validation scores. The validation accuracy peaks at gamma equals 1. Therefore, gamma equals 1 seems to be the best choice, making the statement true. This examines the relationship between training and validation accuracy and model complexity. Notice that across all gamma values, the training accuracy is consistently higher than the validation accuracy. This persistent difference indicates a potential overfitting problem caused by excessive model complexity. Therefore, this statement is true. This problem explores how changing the gamma hyperparameter in a support vector machine, SVM, with a radial basis function, RBF, kernel affects the model's performance. Gamma controls the influence of a single training example. A small gamma indicates a large radius for the influence of each point and thus a smoother decision boundary. A large gamma indicates a small radius, which can lead to a more complex, less smooth boundary. We'll investigate this using training and validation accuracy scores. The dataset is not explicitly described but is implied to be the data used to train and validate the SVM model. The focus here is not on the specifics of the data but on the model's performance, as measured by training and validation scores. This is the data used to train the SVM model. The provided training scores reflect how well the model learns this data for different gamma values. This is a separate dataset used to evaluate the model's performance on unseen data. The validation scores indicate how well the model generalizes to new, untrained data. The model used is a support vector machine, SVM, a powerful classification algorithm. The RBF, radial basis function, kernel is a type of kernel function used in SVMs, creating a nonlinear decision boundary. Gamma is a hyperparameter in the RBF kernel of the SVM. It controls the width or influence of the Gaussian kernel. Tuning this hyperparameter is crucial to finding the best model. These are the different values of gamma used to train and evaluate the SVM model. We'll compare the performance of the model at each value. These scores represent the model's accuracy on the training data for each gamma value. The scores show how well the model fits the training data. Higher scores indicate better fit. The scores are 0.85, 0.88, 0.90, 0.92, 0.93, 0.91, 0.95, 0.96, 0.94. These scores measure how well the model trained on the training data performs on unseen validation data for each gamma value. The scores reveal the model's ability to generalize. Higher scores indicate better generalization ability. The scores are 0.78, 0.82, 0.80, 0.85, 0.87, 0.86, 0.80, 0.79, 0.77. This involves comparing the training and validation scores to determine the optimal gamma value and to detect potential overfitting. This is the core of the quiz. This problem uses Ascalerns validation_curve function to find the best hyperparameter, gamma, for a support vector machine, SVM, with an RBF kernel. We'll examine how changes in gamma affect model performance. The specific dataset used isn't detailed, but it's important to note that the performance metrics presented depend entirely on the characteristics of this underlying data. An SVM is a powerful classification algorithm. The RBF, radial basis function, kernel is a popular choice in SVMs, allowing the model to handle non-linearly separable data. It maps data into a higher dimensional space to make classification easier. Gamma is a crucial hyperparameter in the RBF kernel. It controls the influence of a single training example. A higher gamma means the model is more sensitive to individual data points, leading to potentially complex decision boundaries. This is a function from the scikit-learn library. It's used for hyperparameter tuning. It systematically evaluates model performance across a range of hyperparameter values, providing both training and validation scores, helping to detect overfitting. These scores, 0.85, 0.88, 0.90, 0.92, 0.93, 0.91, 0.95, 0.96, 0.94, show how well the model performs on the data it has already seen. Higher scores are better. These scores, 0.78, 0.82, 0.80, 0.85, 0.87, 0.86, 0.80, 0.79, 0.77, indicate the model's performance on unseen data. These are crucial for evaluating generalization ability. These are the values of the gamma hyperparameter used in the experiment. We see how the model behaves with different levels of sensitivity to individual data points. This is the actual data representing training accuracy for each of the three gamma values. We can see that the training accuracy increases as gamma increases. This is the actual data showing validation accuracy for each of the three gamma values. We can observe a peak in accuracy, followed by a decrease, as gamma increases. Here, we need to compare the training and validation scores to understand how the model generalizes and to choose the best gamma value. By comparing training and validation scores, we can identify overfitting and find the optimal gamma value that balances model performance and generalization. This is done by checking if there is a significant difference between the training and validation scores as gamma increases. Based on the analysis, a suitable gamma value is selected, leading to the final choice of the model. The selection should be based on validation scores, not the training scores, to minimize overfitting. This problem involves using the validation_curve function from scikit-learn to find the best setting for the gamma hyperparameter in a support vector machine, SVM, with an RBF kernel. We're basically trying to fine-tune the SVM to get the best accuracy without overfitting. The specific dataset used isn't detailed, but it's important to understand that the results obtained from validation_curve will be dependent on the data used to train and validate the model. This is a function from the scikit-learn library in Python that's used for hyperparameter tuning. It systematically evaluates a model's performance across a range of hyperparameter values, providing both training and validation scores. It helps us see how changing a setting affects the model's ability to learn from the data and generalize to new, unseen data. These are the accuracy scores the model achieves on the data it was trained on. High training scores are good, but only up to a point. These scores indicate how well the model trained on one dataset performs on a separate, previously unseen dataset. They provide a more reliable measure of the model's ability to generalize. The goal is to have validation scores as close as possible to the training scores, to ensure we are not just memorizing the training data. Gamma is a hyperparameter in the RBF kernel of the SVM. It controls the influence of each data point. These are the three values being tested to determine which gives the best model performance. These scores show the model's accuracy on the training data for each gamma value. Notice the accuracy increases as gamma increases. These scores show the model's accuracy on the validation data for each gamma value. Note that the validation accuracy increases from gamma equals 0.1 to gamma equals 1, but then drops. This is a key indicator of model behavior. This is the core question of the quiz, asking you to interpret the results from the training and validation scores and relate them to the hyperparameter, gamma. Let's analyze and see what's going on here. This statement is false because while training accuracy increases with gamma, validation accuracy shows a peak at gamma equals 1, then it decreases. This statement is true. The increasing gap between training and validation scores as gamma increases is a clear indication of overfitting. The model is learning the training data too well but not generalizing well to new data. This is true. Gamma equals 1 produces the highest validation accuracy. This is true. This difference is another indicator of overfitting, hinting at a potentially too complex model that's fitting the training data too closely.